Hey guys, I'm podcasting the solutions to Lab 5.1. The name is Ramsey. And in the pre-lab notes, I believe I gave you guys, we just talked about the equation for 3a, the before and after equation, which says that P1V1 equals N1 times N1T1 equals P2V2 times N2T2. And talked about some rules. And the first rules was that degrees Celsius should always be turned to Kelvin, and all other units must stay the same on both sides. So if you happen to have milliliters over here, it's going to come out in milliliters over here. Likewise, if you happen to be using torr, it's going to come out in torr. The only thing that has to stay the same is temperature in Kelvin. Okay, here we go. Let's go through these questions. According to the statement above, what was the volume of the gas inside the soda? So if you looked on the can, so let's go back to our statement, actually. Sorry. So here, initially the gas inside the can occupied a volume of 355 milliliters, and the temperature, we'll say, was 25 degrees Celsius. Now your values here might be a little bit different. And what volume of the gas does the soda can occupy upon cooling to? We'll say that it cooled to 0 degrees Celsius. That was the ice bath. Okay. So according to the statement above, what was the volume of the gas inside the can after cooling? So after is our before and after word. P1V1 over N1T1 equals P2V2 over N2T2. Okay, so we know that the moles was constant because it was a sealed container. And we know that the pressure was constant at 1 atmosphere throughout. So this is our new equation. V1 over T1 equals V2 over T2. And for those of you that are interested, this is called Charles' law. Okay. If you plot volume versus temperature, it's a direct relationship between the two. That is, as temperature increases, so does volume and vice versa. So let's solve it. The initial volume was 355 milliliters. The initial temperature was 298 Kelvin. That multiplied by the final temperature, which was 273 Kelvin, is going to equal V2. So I'm going to go to my calculator, and I'm going to type 355, clear that out, 355 times 273 divided by 298 equals 325. So in this case, V2 for me was 325. Now remember what I said initially when we talked about this. If the volume that goes in is milliliters, the volume that comes out is going to be milliliters. So what went in here was milliliters. What comes out is definitely going to be milliliters. When the water was cooled, its phase changed from a gas to a liquid. So when a gas turns into a liquid, that's called condensation. So what is the name for that phase change? We answered that. Please draw and label a phase diagram. So let's do that first. P, T, solid, liquid, gas. Please, and draw an arrow to represent this change. So gas can go to a liquid two ways, either by increasing the pressure or decreasing the temperature. So in this case, we did this by actually decreasing the temperature. We put it in the ice bath. So we're going to have a horizontal line here showing that pressure stayed constant at 1 atmosphere, atmospheric pressure, but the temperature dropped from your 298 Kelvin to 273 Kelvin. Okay. Initially, the water was a liquid. When placed in the can, the water had to be vigorously heated to change its phase. So please draw the Lewis structure for water. So we know that water is bent, 2 sigma bonds, sp3 hybridization, 104.5 degree bond angle, polar with hydrogen bonds. And use what we know about IMF forces or intermolecular forces to explain the same things. So water is polar with IMF, the intermolecular forces that are hydrogen bonding. Okay. Thus, H2O is not an ideal gas and must be vigorously heated to evaporate. Okay, it's got a high specific heat as well from last year, if you remember. It takes a lot of energy to heat it. This is really the reason why. It's a very sticky molecule. Okay, guys, take care. Hope you enjoyed this. Bye-bye.